Okay, now that we've got the theory of surfaces, we understand the equations of them, we understand how to get insight using traces, let's do some problems to understand surfaces, and in particular to understand quadric surfaces. So the first one is we're going to take an equation, we want to put it in reduced form, and we want to understand what is this surface. And the identity that we're going to use is completing the square. You know that whenever you have x squared minus 2ax, you can write this as x minus a squared. That gives you x squared minus 2ax plus a squared minus a squared. And if you had a plus there, you would just have a plus there, and it's the same thing. So this is what's going to allow us to absorb the 4y and the 24z to get this thing into standard form. So first thing we do is we just group our terms. We put all the x's together, all the y's together, all the z's together, and I factored out a 4 from the z's. Then we complete the square. Instead of y squared minus 4y, we take y minus 2 squared minus 4. Instead of z squared minus 6z, we replace that with z minus 3 squared minus 9. And now we notice that 4 times 9 is 36. So that cancels this 36. And we're left with 4z squared plus y minus 2 squared plus 4 times z minus 3 squared. And I put this 4 over on the other side, equals 4. And we can divide through by 4. And now we've got this in standard form. We got x squared over a squared. So this is x squared divided by 1 squared. Plus y squared over b squared. Well, it's not exactly y squared. It's y minus 2 squared over b squared plus z minus 3 squared over c squared equals 1. And this is an ellipsoid. Its center is at 0, 2, 3. And its parameters are a equals 1, b equals 2, and c equals 1. Okay, our next problem is we want to find all points that are equidistant from a point f, negative 1, 0, 0, and a plane, x equals 1. Now this should remind you of a focus and directrix, except that we're in 3 dimensions now, so it might get a little bit more complicated. Okay, but just like doing the focus and directrix, we want all the points P, x, y, z, whose distance to f, let's call it L, and whose distance to the plane, let's call it D, are the same. So L, you just get the distance by the Pythagorean theorem. You take the difference between x, y, z and negative 1, 0, 0, and you add the sum of the squares. And the distance to the plane is just x minus 1, absolute value. And we want to set these equal, and the easiest way to do that is to set their squares equal. And so L squared is x plus 1 squared plus y squared plus z squared, and d squared is x minus 1 squared. And then we just expand everything out, and we see that the x squareds cancel. Whoops, that should be a 1. And the 1 cancels against the 1 on this side. You put the x's on the other side, you just get y squared plus z squared equals minus 4x, or x equals minus y squared plus z squared over 4. This is a paraboloid. If we just looked at a trace and we fixed the value of z, we'd get x's going as minus y squared over 4. We fix the value of y, we get that x goes as minus z squared. If we fix the value of x, we get that y squared plus z squared is a constant. So this is an elliptic paraboloid. And the picture we can get by doing a trace. Let's look at what happens when z equals 0. When z equals 0, we're in the xy plane, and we want all the points that are equidistant from negative 1, 0, negative 1, 0, 0, but negative in the plane that's just negative 1, 0, and the line x equals 1. Well, that is the focus directrix definition of a parabola, and we get the parabola x equals minus y squared over 4. And then all that happens with the third dimension is what we've done is we've taken this parabola and we've rotated it around the x-axis. So we get the paraboloid that you get by rotating a parabola around its axis. Okay. Our final problem is to use traces to identify the surface 9x squared minus y squared plus z squared equals 1. And the first thing we want to do with traces is we look at horizontal traces. We imagine that z is a constant and see what it looks like in the xy plane. So we put a z on the other side and we say, hey, it's 9x squared minus y squared equals 1 minus z squared. In particular, if z equals 1, we get 9x squared minus y squared equals 0. And we get the lines y equals 3x and y equals minus 3x. Now, if z is less than 1, then we get a hyperbola on this side. So this might be, say, z equals 0. This might be z equals a half. This is z equals a half. This is z equals 0. And when z is bigger than 1, you get a hyperbola on this side. So you see that whatever happens, you're going to get something with hyperbolas in it. Now you get even more insight if you look at the traces where you hold y fixed. If you put y on the other side of the equation, you get 9x squared plus z squared is 1 plus y squared. If you set y equal to 0, that would give you an ellipse. If you set y equal to anything other than 0, it still gives you an ellipse, only the radius of the ellipse gets bigger and bigger and bigger as y gets bigger and bigger and bigger. So we've got an ellipse, and as you move off in the y direction, it grows and grows and grows and grows, and as you move off in the negative y direction, it also grows and grows and grows and grows. So the picture looks like this. In the y, if you fix the value of y, you get an ellipse, and the ellipse grows as y increases in one direction. It grows as y goes negative. If you slice it vertically, if you slice it with a horizontal slice, if z is bigger than 1, you get a slice up here, and that gives you a hyperbola. If you have a slice with z less than 1, you get the hyperbola pointing the other direction. So this is called a hyperboloid of one sheet. If you slice, because some of its traces are hyperbolas, but it's all in one piece. And that is our surface.